Okay, minasan, konnichiwa, Samurai Engineer desu. So, let us talk about some problems and explain them using what we learned in establishing a very good approximate design method for continuous slab and by using ACI coefficient. Okay. So, but before that, let us allow somebody to confirm clarity of sound. Okay, clear po, sir, according to Cyrene. Okay, so let's continue. Therefore, I will just make a message on our GC to remind others of the importance of this subject. Currently, we are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so concurrent participants. So I have what? I have the function that I can see the participants, but I will allow Daniela to take a screenshot so that we have an evidence. So evidence is one thing, but I know who are really serious, and if you are serious, I will be serious in helping you, and if you are not serious, I will not be serious in giving you the grades. Okay, So remember, okay, I could not be very serious in giving you the grades. Anyway, let us proceed for the benefit of those who are here to learn. Okay, and I am one of them. I want to learn. I want to help those who want to learn. Okay, the example in designing a continuous slab of the given figure, we have a given figure that I will show you later. Design that continuous slab for moments calculated using ACI coefficients. So the slab is to support a service live load 165 and a superimposed dead load of 5 PSF in addition to its own dead weight. Okay, so 5 plus dead weight, and FC prime 3000 psi, FY 40,000 psi. The slab is to be constructed integrally. So integral, no? Meaning beam, slab, column is integral with its spandrel girder. So spandrel girder supports and spandrel supports are 12 inch wide. Okay, 12 inch wide. So let me show you therefore the figures. So this is the figure. This is the given figure. So we have 13 feet, 13 feet, 13 feet. So everything 13 feet. That is clear span. That is clear span. What is the dimension from this to this? That is 12 inches, 12 to 24 given here. This is 12 rather 12 inches. Okay, so 12 inches wide. So this is 12, 12, 12, and 12. So 12 inches, that is 300 mm. So a very a common size of beam width. Okay. Also for column, that is also common. Okay. So we have first interior support. So we can get the following. Okay, so positive and negative moment. So as you can see here, first the positive moment. So positive moment, we have 3 types. So what are those? So let us have the interior. Interior is 1/16. So correct, 1/16. Then the end span 1/14. So the end span 1/14. Okay, with integral, no? Integral beam and slab. Okay, 1/14. We do not have a given cantilever, so we do not have 1/11. So for the positive side, 1, 2, 3. There are 3 of them. So 1, 2, and 3. So 1/14, 1/16, 1/14. Okay. So next, let's go to the negative. Okay. So the negative, we have again this side and this side. So this side is others. This side others. This is the exterior face of the first interior support. Okay. So what do you have that? No. Interior face of the first interior support. That is 1/11. here. 1 over 11, 1 over 10, 1 over 11, 1 over 10. Okay, so here we can show 1 over 10, 1 over 10, and 1 over 24 is the here, 1 over 24 here. So the exterior support the interior face. Interior face of the exterior supports here, 1 over 24. Okay, so 1 over 24, 1 over 24, 1 over 10, 1 over 10. Okay, where is the 1 over 11? So 1 over 11 here. Here is the 1 over 11 here. 1 over 11 and 1 over 10. Okay, so 1 over 11 here, 1 over 11 is on the interior. Exterior is 1 over 10. Okay, so you have what? This one, 1 over 10 is exterior of first interior support. 1 over 11 is the other face. Okay, but if you can compare 1 over 11 and 1 over 10, which one is larger? 1 over 10 is larger. That's why we use 1 over 10. Okay? So we use 1 over 10 rather than 1 over 11. Because here, okay, 1 over 11, 1 over 10, 1 over 11, 1 over 10. So then use 1 over 10 because it is larger. Okay? Do we follow? We follow. That's why we have 4 negative moment values and 3 positive moment values. Everything are coefficients of WL squared. Everything WL squared. We know that L is equal to 13. Am I correct? I am correct. 13. So 13 is L. So L squared. And W. We can calculate the W. So we can compute the value of W by live load and dead load combination. Okay. Therefore, okay, going back here, so minimum T for deflection by ACI code, note that this table uses L, not LN. Okay, the deflection multiplier for 40, grade 40, still 0.4 plus 40 divided by 100, that is 0.8. Okay, for deflection. So minimum T for end span and minimum T for interior span. So these are for code section 9.5.2.3 for the minimum value of T, thickness. Okay, so we can estimate that. So 0.8, therefore 0.8 L over 24. Then for interior span, 0.8 L over 28. Okay, so then therefore L with what? This is conversion factor. This is what? 13 foot plus 12 inches, that is 1 foot. So 13 plus 1 is 15. Because we are using L, not LN. So this is equal to 5.6 inches. So on here we have, again, L is 13 plus 1. 13 plus 1 again. Here, this is 13. This is 1. 1 foot is equal to 12 inches, this one. So that's why it is from center to center, that is 14. Okay, 13 plus 1. Okay. So that's why we have here, then divide by 28 this time because we are interior. So these are for the thickness. Okay, so 5.6 versus 4.8. So we can choose what? 6 inches, because 6 inches is greater than this one. Okay, do you follow? So 6 inches slab. 6 inches slab in mm, that is 150 mm. That is normal. That is an ordinary type of slab. Okay. Then load and maximum moment for a 6-inch slab. Okay. So we just determine the value of the slab. Okay. Take note of this process for slab. Okay. Okay. To be able to estimate preliminary this value. Okay. So we already know the thickness, so we can even estimate the dead load, no, due to self weight. You can even do that. So 0, 4, and 1. 0, 4, 1. So let's proceed. So therefore, dead load, so slab weight, for the slab alone, how much is one foot is 12 inches. So therefore, you can just divide. So 6 divided by 12, that is 1/2 foot. Then 150 is from the table. That is the value of the table for dead load. That is concrete. Okay. So concrete 150. So therefore, 150 divided by 2, that is 75 pieces. Okay, dead load. For this is dead load, that is weight of the not included the pipe. So we have the given here. Don't be confused. Dead load is pipe. Okay, in addition to its own weight. So live load 165. Do we have here 165 here? 165. So therefore, we can compute. So 1.2 times dead load plus 1.6 times live load. So therefore, 360. 360 is our W, therefore moment. Okay, so we have 1/10 WL squared. 1/10 is our coefficient. What is this? 360 is our calculated load times 13 squared. Okay, so take note, LN here. Okay, LN, clear distance. So 13, not 14. Okay, so in estimating the thickness, we have L. Take note of the difference. L versus LN. So L is the center to center distance, span. Okay, but LN is clear distance. Okay, so clear distance squared. So we have this moment maximum. Okay, so as you can see here, which one has the highest 1 over 10 is the highest compared to 1 over 24, 114, 116. So 1 over 10. Okay. So you can compute this. Okay. So what did we arrive at as our answer here? Here. Moment is 6084. Okay. Moment is 6084. So here is our moment 6084. So showing you how to calculate this. So also calculate this one, calculate this one, calculate and calculate. So calculate all of this moment. So after that you can what? Determine the resistance. So resistance is mu divided by pi BD squared. That is the resistance. So resistance in PSI. So there are 7 values. 3, 3, and then 7. Just divide by BD squared. So we already know the B. D, okay? So we have that, and therefore we can find out the value of what? Rho of the steel ratio. This is the steel ratio. So this is the steel area. The steel area that we can determine from this. Okay. Okay, determine the computing moments. So you have to compute all of them. Then after that, compute the rho. Okay, using the moment. Okay, we can compute the rho. Then, therefore, after computing the rho, we can compute the area of steel. Then after that, we can select the reinforcement. Okay, so that's how we do this. Okay, so it is not shown on the solution in details, but only shown up to moment, because we already know how to calculate from moment to rho. So by using this one, so we have what? Resistance. Okay, so we found out the resistance, so we have the formula. Rho is equal to something square root to so then Rn. So Rn is our resistance here. Okay, so we have that formula for rho. Okay. So the minimum values of rho here specified in ACI for tensile steel are applicable to both positive and negative. They are applicable to both positive and negative because there are steel here that are compressive. Okay, compressive are for positive. Positive moment, they are compressive. Okay, wait. So here, the moment looks like this. So the tension side is the positive. Okay? Tension, positive, tension. So here, meaning here. Okay? So we have the what? This is the reinforcement on tension side. It's the reinforcement. Tension side here. This is the tension side. In between this one, tension side. So this is also tension side. Tension side. Then another one, tension side. Then another one, tension side. Okay? So, what about this? This is compression side. Compression side. Compression side. Compression side. Okay? So, for tension side, so we have this one. But here, this is still tension side. Tension side. So, number 5 at 6 inches. Number 5 at 6 inches. Okay? Alt bend. Alt bend. So, symmetrical about center line. So, symmetrical. So, the bar selected, okay, according to this area of steel. 5 at number 12.31. 5 at number 6.61. 5 at number 6.61. 5 at number 6.61 and so on. So, for this one, this one, this one, this one. So, they are the same, no? Same. Okay, so again, this is the tension steel reinforcement. So, this one. So, this is the compression steel reinforcement. This one, this one, this one, and this one. Okay? Do you follow? So, this is actually the procedure of computation. This is the procedure for computation. First, use the coefficient. After coefficient, you can now calculate the moments. Then after the moments, calculate the resistance. After resistance, calculate the rho or the steel ratio. Then after the steel ratio, we can calculate the area of steel. And then select the proper size of the reinforcement. So that is the procedure in dealing with this problem, wherein we are being asked to design the continuous slab for moments calculated with ACI coefficient. Okay. So for slabs, we are not concerned with the design of web reinforcing. For continuous beams, however, web reinforcing must be carefully designed. Such designs are based on maximum shear occurring at various sections along the span of a continuous beam. From previous discussion, you will remember that to determine the the maximum shear occurring at section, okay, the uniform dead load would extend all across the span, while the uniform live load would be placed from the section to the most distant support. Okay, this is how you deal with it, so that there is a imbalance, and we can get the maximum reaction from the element. Okay. So for example, here, position of live load for maximum shear, we can have this live load and dead load. Okay. So do not put any live load here. Just stop at that section wherein we want the critical section. Okay. A shear diagram. How about a shear? So this is what we want. 1.15. Okay. Here, this is 1. This is 1.15. WL over 2. So this is what we have on our ACI. This is our ACI coefficient. So 1.15 here, 1 here, 1. So 1 and 1, we have what? Straight line. So 1.5. So we have 1.5. If we have the center as neutral Okay, so this is shear diagram resulting from the use of coefficient. There are only two coefficients, 1.1 and 1, times the shear, which is WL over 2. So that means we have those values. Okay? So this is another one for frame, equivalent frame method. Okay, so let us immediately discuss for the equivalent frame method. So example number 2. Okay. Equivalent rigid frame method. When the continuous beam frame are supported by girders, the normal assumption made is that the girders provide only vertical support. So we have what we call torsional moment, this one. So analyzing such reinforced concrete, wherein we are going to study the beams frame into columns, the beam bending stiffness of columns together with the torsional stiffness of the girders. Okay. We have what we call equivalent rigid frame method. So let us apply this method into the example. So as you can see here, continuous with only vertical support. Okay, pin support, and then another pin support. 1, 2, 3, 4. So 4 span. So like this one. This is the vertical and rotational support. So example number 2. Using equivalent rigid frame method, draw the shear and moment diagrams for the continuous T-beam. Okay? Because of the integral slab and beam construction, so we have the beam is assumed to be framed into 16 inches by 16 inches column, and is to support a service dead load 2.33, including the beam weight, and a service live load of 3.19. Assume the live load is applied in the center span only. The girders are assumed to have a depth of 24 and a web depth of 12. Web depth or girders depth. Okay? Assume that the eye of the T-beam equals 2 times the eye of its web. Okay? Let us proceed computing fixed end moments. Okay? So first and third, we have the following. First and third. Okay? This is the frame. 24, 24, 24 given. Okay? So this from this, they are 12, 12. So again, 24, then 24, 24, 24. So we have the following. Using the equivalent frame method, we are going to calculate the stiffness and carryover factor. So we have that in our structural theory. Okay? How to come up with this structural theory? So I will not do it anymore right there, right here. So please review. Okay? So this type of computation, this is MDM method. So the MDM method, we have this MDM method. So as you can see, finally you will reach these values wherein those are our required. So here, okay. So therefore, we have 24, 42, 94, 94, 42, and this one. So just like this. Okay, so this is our shear. Okay, shear. So these are in moment. So shear in moment. How to look into these are in shear moment. So therefore, MDM method. So from this one, so negative 37 here, negative. You have 255, so 255 connected to negative 330, negative 330, okay? And then positive 330 here, and then negative 255. So symmetrical, okay? So like this. This is our moment. Moment, this is shear diagram. Shear and moment diagram. Okay? Okay, so do we follow? Those are our answer. Using this stiffness and carryover factors. Okay? So using the moment distribution method or MDM in our theory of structure. This is how we do that. Okay? So that is our answer because we are only asked to draw the shear and moment diagram. So drawing it is only that way. No? So first, what you can do is find out the WU, and then after finding out the WU, W L squared over 12. So find out M. So for the center span, which is larger, so because here we have a condition, okay, that the live load is applied in the center span only. That's why we have this combination at the center span only equal to 7.8. Okay? So using this times L squared over 12, so we have this. Okay? MU. So we have MU for exterior span and interior span. So computing stiffness factor, this is how we compute each and every factors. I of columns 1 over 12. BH cube over 12. Okay, so BH cube over 12. Then K of columns, I over L. So that is K. Okay. So therefore, for columns, we have the following values of K. Then equivalent I of T-beam or T-beam. So we have 2 times that, 2 times this. So therefore, multiply by 2. But what is the H? Now, we have 24. We have 24 here. So we have 24 in our H. For the beam, for the T-beam. Because the thickness is 16. 16 is the thickness. Here, 16 by 16. So 16, okay, and then depth 24. Therefore, we have to use 24 here. Have to use 24 here. Here, 24. Okay. So therefore, we can find out the I for the T-beam. Then for the T-beam, just divide by 24 feet because we have 24 here for the T-beam. So T-beam. Okay, so divide by 24, therefore 1,152 compared to the column. This column. Therefore, those are the value of K. Take a look at the values of K. 455, 1152. So 455, 455, 455, 455. Okay? So those are 455, 455, 455, 455. Okay? Then 1152. So this is the T-beam. T-beam, column. Okay? So complete process. So we have these necessary values. Okay. Then afterwards, then since we already know stiffness, carryover factors here 0.56, 0.36, carryover factors here. Okay, computing those, we can therefore so you can compute this 0.56 from this 1, 2, 3 out of this 3. Then you can compute 0.36 from this 1, 2, 3, 4. Okay, so using our theorem structure, then afterwards you can do this tabulation, iteration. So then afterwards, because of this negative 37.9, that is our moment. This is our moment, and so on. Okay. So then you can also find the shear, or this shear is easier to find. Now, how to find out 69.6? You just find out the area of this. This one. So, multiply 24.54 times 8.76 divide 2. Okay? So, that is the value. Okay? So, I will show my calculator. Okay? So, showing my calculator. Where is my calculator? Here. So I can show you my calculator. Okay. Here. Multiply 24. What is 24? Here. 24 here. 24.54. 0.54 multiply by 8.76. 8.76, then divide by 2 times 8.76 divided by 2. That is 107. Okay? So, 107, you have, take note, 107 is from this lower point to the maximum. So, therefore, minus 37.9. Where can you find the 37.9? Here. We already find it. Here. So, minus 37.9. Subtract. Okay? So, minus 37.9. That is 69.6. Okay? So, that's how you can find out the positive value. Okay? Okay, are we clear? Any question? So, everything is clear, clarified from this example. Okay? Do you have any other question? So, right now, we are only 3. There are only 3 students. Okay? So, after taking the attendance, there are only 3 students right now. So, there are only 5 students right now. I can see the student. Okay? There are only 6 students. Okay? I don't know. Anyway, I am not particular with attendance. Okay? So, but I can see you. I know who you are. I can even call your name. Okay? Right now. There are only 1, 2. How many are there right now? Kagiya, Kapulong, De La Cruz, Tabes, Saranya, Hunyo, Balsada, Peras. So those are currently inside the room. Okay? So I know who you are. Humabol si Zakaria. So I know who you are. Okay, so anyway, any question? Any question? Sir, 23 po, 22. So, yan yung nakikita sa inyo kasi di yan totoo. So, participants, yan yung totoo kung ilan yung participants. So, meron ako dito apps na participants. So, yung participants, yan yung naka-online right now. So, right now, naka-online 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yung andito mismo sa live stream. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. Hindi yung nakalagay dyan sa concurrent viewer. That is not the real thing. Okay? Okay? So, because on concurrent viewers, that is average. It is being averaged in some time duration. So, that is not instantaneous. So, what I'm seeing is instantaneous. I can go back and forth. Okay? I can even record your timestamp. Okay? But I'm not very particular with that. You can claim that you are here and okay. But Let us take a break if there are no question. So I don't care if sir nasa 20 plus na po. I don't care. Okay? So I am seeing who are connected in this, who are listening here. Okay? I don't care. We can even find out on the result of final exam. We will have face-to-face probably tomorrow. Okay? I will post the important information face-to-face final exam. Let's confirm what we did for one semester. Do we really learn? Okay? Or do we just try to show up for attendance? Okay? So we will have that soon. We can answer that very soon. Who learned and who just came in for attendance. So again, let us take a break and get back on next live stream. This is your Professor Dr. AP, Preaching Engineering for Nation Building. By the way, you can just review portal method. So there are two methods of frame analysis in theory of structure, so that you are well informed. If we have a problem that you can use portal method, you can use portal method. This is an area for theory of structure. This must be part of theory of structure. Portal method. That is how it is done. Actually, we already come up with, so we will not do the portal method here. Rather, you have to review it on your own. So that's all for, again, for this topic. Okay, so none, sir. Meaning no question. Okay. Sir, nasa 20 plus na po. Okay. I will let you prove it. Dexter Robin Webb. So how much you learned in the face-to-face exam. So I am not particular with attendance. Everybody, I will let you prove during the final exam. So whether you want it to be 20 na po, sir. Well, okay, it's 20. You can say it. It's 20 or not. I do not even care if only one student come up. If one student come up, I will still make a lecture. I do not care. I don't care. because I'm here for those who want to learn and not for those who want to get the attendance. Okay, so that's the difference. That's why I will always be here.